Yellowstone has spent decades sitting at the center of one of geology's most enduring mysteries. Beneath a landscape filled with geysers, boiling springs, mud pots, and restless ground lies one of the largest volcanic systems on Earth. Yet, despite generations of research, a surprisingly basic question has remained unresolved. What exactly keeps feeding the enormous reservoir of heat beneath Yellowstone? Is the volcano powered by a deep column of hot rock rising from the depths of the mantle, or is something else happening beneath North America entirely? New research is forcing scientists to reconsider assumptions that have shaped Yellowstone geology for years. The emerging picture is not one of a simple vertical plume punching upward from deep inside Earth. Instead, it points toward a far more complicated engine driven by tectonic forces, shifting crust, migrating magma, and an intricate network of pathways extending through the lithosphere. Yellowstone may not merely be sitting above a giant blowtorch from Earth's interior. Its volcanic system may instead be sustained by the slow mechanical stretching and tearing of the western United States itself. That possibility carries implications far beyond one national park. Yellowstone is often discussed as a singular geological phenomenon, but it exists within a broader tectonic framework that stretches across much of western North America. Understanding how magma reaches Yellowstone means understanding how continents deform, how mantle material moves, and how volcanic systems evolve over millions of years. The traditional explanation for Yellowstone's volcanism emerged from a concept known as a mantle plume. In this model, a narrow column of exceptionally hot rock rises from deep within Earth's mantle, potentially from depths approaching the core mantle boundary. As the plume ascends, pressure decreases, allowing partial melting to occur. Magma generated from this process eventually reaches the crust and fuels volcanism. For many years, Yellowstone appeared to fit this model reasonably well. One of the strongest pieces of evidence came from the volcanic tracks stretching across the Snake River Plain. Moving southwest from Yellowstone, geologists can trace a chain of progressively older volcanic centers extending across southern Idaho. This sequence resembles the volcanic chains produced when a tectonic plate moves over a stationary hotspot. The concept is similar to the formation of the Hawaiian Islands, where the Pacific plate slides across a fixed mantle hotspot, creating a trail of volcanoes. Under that interpretation, North America slowly migrated southwestward over a deep mantle plume. As the continent moved, volcanic activity shifted northeastward, eventually arriving at its present location beneath Yellowstone. Yet the mantle plume model never answered every question. Seismic imaging studies have struggled to produce a universally accepted picture of a continuous plume extending from Yellowstone into the deepest mantle. Some studies suggested deep structures. Others found evidence that appeared shallower or more fragmented. The deeper scientists looked, the more complicated the image became. Meanwhile, Yellowstone sits within a region undergoing profound tectonic deformation. To the west lies the Basin and Range Province, one of the most actively stretching regions on the continent. Across Nevada, Utah, Idaho, and neighboring states, Earth's crust is slowly being pulled apart. Mountain ranges rise while adjacent valleys sink, creating the distinctive basin and range topography visible across much of the American West. That stretching is not merely a surface phenomenon. It affects the entire lithosphere, the rigid outer shell of Earth comprising the crust and uppermost mantle. According to the new model, these tectonic forces may play a much larger role in Yellowstone's existence than previously believed. Researchers use three-dimensional geodynamic simulations to examine how mantle material, tectonic stress, and lithospheric deformation interact beneath western North America. Their findings suggest that Yellowstone's magma may originate from relatively shallow mantle sources influenced by regional tectonic processes rather than a single deep plume rising from extreme depths. The mechanics are remarkably complex. Western North America is undergoing westward extension. The lithosphere is being stretched, thinned, and weakened. At the same time, remnants of an ancient tectonic plate known as the Farallon Plate continue sinking deep beneath the continent. Although most of this oceanic plate disappeared millions of years ago through subduction, fragments remain embedded within the mantle. As these remnants descend, they exert downward forces on surrounding mantle material. Simultaneously, extension within the basin and range province creates zones of reduced pressure above. Together, these processes may generate pathways that allow magma to rise toward the surface. Instead of a singular vertical plume feeding Yellowstone, magma may be drawn upward through a broad tectonic system shaped by continental deformation. This interpretation helps explain why Yellowstone occupies such an unusual geological position. The Yellowstone Plateau lies near the northeastern edge of the basin and range province. It sits close to the transition between regions experiencing extension and regions characterized by thicker, more stable continental crust. Such boundaries often serve as conduits for magma migration, because differences in crustal thickness and stress create structural weaknesses. The simulation suggests that mantle material southwest of Yellowstone undergoes partial melting before migrating northeastward beneath the volcanic system. Rather than rising vertically from great depth directly beneath the caldera, magma may travel laterally through the upper mantle before accumulating beneath Yellowstone. This distinction matters because it fundamentally changes how scientists think about volcanic plumbing. Volcanoes are often imagined as having simple structures, a magma chamber beneath the volcano connected to a deeper source. Reality is rarely that straightforward. Modern geophysical imaging increasingly reveals extensive networks of partially molten rock distributed across large regions. Magma reservoirs can be interconnected, mobile, and constantly evolving. Yellowstone appears to exemplify this complexity. Recent seismic studies have provided some of the clearest images yet of the system hidden beneath the national park. Using controlled seismic sources and advanced imaging techniques, researchers identified a sharp boundary approximately 2.4 miles, or 3.8 kilometers, beneath the northeastern portion of the Yellowstone caldera. This boundary marks the top of a volatile-rich zone associated with the magma reservoir. The discovery offers an extraordinary glimpse into the internal architecture of the volcanic system. Instead of finding a gradual transition from solid rock into molten magma, scientists observed a remarkably distinct reflective layer. Evidence suggests that this zone contains a mixture of magma, supercritical fluids, and gas bubbles occupying pore spaces within partially molten rock. In practical terms, Yellowstone's magma reservoir appears capped by a volatile-rich layer acting somewhat like a pressure-regulating boundary. This layer may play a crucial role in preventing catastrophic pressure accumulation. Gas released from ascending magma can escape through fractures and permeable rock above the reservoir, gradually venting pressure rather than allowing it to build toward explosive levels. Researchers have described the process as analogous to a breathing system in which gases continually migrate upward through the crust. That breathing behavior helps explain one of Yellowstone's most visible characteristics: its immense hydrothermal activity. The park contains roughly half of the world's active geysers. Thousands of hot springs, fumaroles, and thermal features dot the landscape. These surface expressions reflect the enormous heat flux rising from below. Water infiltrates through fractures in the crust, descends toward hot rocks, heats dramatically, and returns toward the surface. Along the way, it transports dissolved minerals, gases, and thermal energy. The newly imaged volatile-rich cap suggests that gas migration through the crust may be even more important than previously recognized. Rather than indicating imminent eruption, Yellowstone's persistent gas emissions may represent a stabilizing mechanism allowing the system to release energy continuously. This emerging understanding also reshapes views of magma storage beneath the caldera. Popular depictions often portray Yellowstone as containing a giant underground ocean of molten rock waiting to erupt. Geophysical evidence paints a different picture. Most of the reservoir consists of crystal-rich material rather than fully liquid magma. The system resembles a vast mush zone containing varying proportions of crystals, melt, gases, and fluids. Only portions are sufficiently molten to behave as mobile magma. Large eruptions generally require melt fractions much higher than those presently observed. This distinction is important because the presence of magma alone does not mean eruption is imminent. Volcanic systems can remain active for hundreds of thousands of years without producing major eruptions. Magma may enter reservoirs, cool, crystallize, release gases, and evolve chemically without ever reaching the surface. Yellowstone's history demonstrates this clearly. The volcanic system produced 3 enormous caldera-forming eruptions during the past 2.1 million years. The oldest occurred approximately 2.1 million years ago. Another followed around 1.3 million years ago. The most recent caldera-forming eruption occurred approximately 631,000 years ago. These eruptions expelled extraordinary volumes of volcanic material, reshaping landscapes across vast regions of North America. Yet the intervals between them were not regular. Geological systems rarely operate on precise schedules. The common public perception that Yellowstone is somehow overdue for eruption misunderstands volcanic processes. Magma generation, storage, and eruption depend upon evolving conditions rather than predictable clocks. The newer tectonic-driven model reinforces that idea. If Yellowstone's magma supply depends heavily on regional deformation and mantle flow rather than a single persistent plume, then the volcanic system may respond to a broader set of geological processes than previously assumed. Magma generation could vary according to changes in lithospheric stress, mantle circulation patterns, and crustal architecture. One intriguing aspect of the new research involves the concept of mantle flow. Earth's mantle is not static. Although solid on short timescales, it behaves like an extremely viscous fluid over millions of years. Temperature differences, density variations, and tectonic forces drive slow circulation throughout the mantle. The simulations suggest that mantle material beneath western North America may be moving eastward in a broad flow sometimes described as a mantle wind. As this material encounters variations in lithospheric thickness, stresses develop that can help localize melting and magma transport. Rather than requiring a narrow plume ascending vertically, Yellowstone's volcanism may emerge from interactions between moving mantle material and a tectonically weakened lithosphere. This perspective aligns with growing recognition that many volcanic systems may not fit simple classifications. For decades, geologists often divided volcanoes into categories such as hotspot volcanoes, subduction-related volcanoes, or rift volcanoes. Increasingly, evidence suggests significant overlap among these mechanisms. Yellowstone may represent an example of multiple processes operating simultaneously. Deep mantle influences may still exist. Tectonic extension clearly plays a role. Lithospheric structure affects magma migration. Volatile behavior influences reservoir stability. Rather than a single cause, Yellowstone likely reflects the interaction of numerous geological systems operating across vastly different scales. The volatile-rich cap discovered beneath the caldera provides another reminder of this complexity. At depths of approximately 2.4 miles or 3.8 kilometers, pressure conditions allow dissolved gases within magma to separate and accumulate. This process, known as volatile exsolution, strongly influences eruption dynamics. Gas bubbles increase magma buoyancy, modify viscosity, and affect pressure conditions within reservoirs. Many explosive eruptions occur because gases become trapped within ascending magma. As pressure decreases, bubbles expand rapidly, fragmenting magma and driving violent eruptions. Yellowstone's cap appears to function differently. Evidence suggests gases are escaping through fractures rather than accumulating catastrophically. The reservoir therefore behaves less like a sealed pressure cooker and more like a system capable of gradual release. Scientists achieved this discovery using an impressive combination of technology and fieldwork. Researchers generated controlled seismic waves using specialized equipment capable of transmitting vibrations into the ground. By analyzing how those waves reflected from subsurface structures, they constructed high-resolution images of the magma reservoir's upper boundary. The method effectively created thousands of tiny artificial seismic signals that illuminated features previously hidden from view. Such advances represent a broader revolution in volcanology. Only a few decades ago, much of what scientists knew about volcanic interiors came from indirect evidence. Today, seismic tomography, Geodetic monitoring, satellite observations, gas measurements, and sophisticated computer simulations allow researchers to examine volcanic systems in unprecedented detail. Yellowstone has become one of the world's most intensively monitored volcanic regions. Instruments continuously track earthquakes, ground deformation, gas emissions, and thermal activity. These observations reveal a dynamic landscape. The caldera periodically rises and falls by several inches or centimeters as magma and fluids move beneath the surface. Earthquake swarms occur regularly. Hydrothermal features change behavior. New vents sometimes emerge while others become inactive. None of these processes necessarily indicate impending eruption. Instead, they reflect the normal behavior of an active magmatic system adjusting to shifting pressures and fluid movements. The new tectonic model helps place these observations into a larger geological context. If Yellowstone's magma originates through interactions involving lithospheric stretching and mantle flow, then surface activity becomes part of a continent-scale process rather than merely a local volcanic phenomenon. The geysers, earthquakes, and uplift observed within the park may ultimately be connected to tectonic forces operating hundreds or even thousands of miles away. That realization underscores the extraordinary interconnectedness of Earth's interior. A sinking remnant of an ancient oceanic plate deep beneath North America may influence stresses within the mantle. Those stresses may guide magma migration. Magma movement may feed reservoirs beneath Yellowstone. Reservoir dynamics may control hydrothermal activity visible at the surface. Visitors watching Old Faithful erupt are therefore witnessing the surface expression of processes extending through vast volumes of Earth's crust and mantle. Despite these advances, significant uncertainties remain. No single study has solved Yellowstone's mysteries completely. Questions persist regarding the exact depth of magma generation, the geometry of transport pathways, the role of deep mantle structures, and the long-term evolution of the volcanic system. Future research will likely integrate increasingly detailed seismic imaging with geochemical analyses, numerical simulations, and satellite monitoring. Each new dataset adds another piece to a puzzle that remains incomplete. Yet a clear theme is emerging from recent discoveries. Yellowstone appears less like a giant isolated magma chamber and more like a sprawling dynamic network extending through multiple levels of Earth's interior. Magma reservoirs connect to deeper mantle sources. Volatile-rich layers regulate pressure. Tectonic forces create pathways for melt migration. Hydrothermal systems transport energy toward the surface. The volcano's fuel supply may therefore be stranger than many scientists once imagined, not because it comes from a mysterious source, but because it arises from the combined effects of tectonic stretching, mantle circulation, crustal weaknesses, gas-rich magma, and geological processes operating across enormous distances and timescales. The image of a simple plume feeding a giant underground reservoir is giving way to a far richer and more intricate picture. Far beneath Yellowstone's forests, rivers, and geothermal basins, the continent itself appears to be participating in the volcano's operation. Ancient plates continue sinking. The western United States continues stretching. Mantle material continues flowing. Magma continues migrating through hidden pathways. Gases continue escaping through fractures. Heat continues rising toward the surface. The result is one of the most closely watched volcanic systems on Earth, sustained not by a single mechanism, but by an evolving geological machine whose complexity scientists are only now beginning to fully appreciate. An additional implication of the research involves the broader history of Yellowstone's migration across the American West. For decades, the chain of extinct volcanic centers stretching across the Snake River Plain was viewed primarily as evidence of a continent moving over a stationary hotspot. The new model does not necessarily eliminate that interpretation entirely, but it suggests that the volcanic track may have been influenced by changing tectonic conditions as much as by the movement of a deep mantle source. As the crust of western North America gradually stretched and thinned over millions of years, zones favorable for magma generation and ascent may have shifted geographically. In this view, the apparent migration of volcanism could reflect a moving pattern of lithospheric weakness interacting with mantle flow, rather than a simple conveyor belt relationship between a fixed plume and a drifting continent. Such an explanation would help account for some of the irregularities observed in the volcanic record, where the timing and distribution of eruptions do not always conform neatly to the expectations of a classic hotspot model. The role of the lithosphere itself has also gained increased attention. The lithosphere is not a uniform shell of rock. Its thickness varies dramatically across North America. Beneath stable continental interiors, it can exceed 120 miles, or nearly 200 kilometers, in thickness. Beneath tectonically active regions of the West, however, it is considerably thinner. These variations influence how heat moves upward from the mantle and where magma can accumulate. A thinner lithosphere acts somewhat like a weakened section of a pressure barrier. Hot mantle material approaching from below encounters less resistance, making partial melting more likely. Yellowstone sits near a region where these structural contrasts are particularly pronounced. The volcanic system therefore occupies a geological crossroads where mantle dynamics, crustal architecture, and tectonic deformation intersect. Another noteworthy aspect of the research is its potential relevance to volcanic systems elsewhere on Earth. Yellowstone is often treated as unique because of its size and geothermal activity, yet the processes identified in the study may operate in other regions where continental extension coincides with mantle upwelling. Similar interactions between stretching crust and mantle circulation have been proposed in parts of East Africa, the Aegean region, and portions of Western Asia. Understanding Yellowstone may therefore improve scientific understanding of how continental volcanism develops on a global scale. The findings also highlight an important reality about scientific progress. Geological models are rarely discarded overnight. Instead, new evidence gradually refines existing ideas. The mantle plume hypothesis emerged because it successfully explained many observations, and elements of that framework may still remain valid. What is changing is the recognition that Yellowstone's volcanic engine is likely more intricate than any single explanation can capture. Rather than being powered exclusively from below, the system may derive energy from a combination of deep mantle processes and the ongoing tectonic evolution of Western North America. That emerging perspective transforms Yellowstone from a relatively isolated hotspot into part of a vast geological network linking the crust, lithosphere, and mantle across much of the continent.